When estimating the population standard deviation based on a sample, instead of using the sample size n in the denominator, we use n minus 1. There are several ways to conceptualize the reason for this, but the following explanation gets more directly into the math behind it. To start, if we were able to collect data on everyone in a population sized n, the variance would be the sum of xi minus mu squared divided by n. Notice we use sigma squared because it's the population value. We're not estimating it. We also know the mean of the population, mu, or can calculate the exact value because we have data on everyone. In reality, we rarely obtain data on everyone in the population and instead use samples. Now, imagine for a minute that we have a sample of size n, lowercase n, from the population, but still for some reason we know the population mean. In that special case, we can estimate the population variance using the sample size n in the denominator instead of n minus 1. Note that E parenthesis sigma squared means the expected value of sigma squared. This is unbiased because we can still use the population mean. Keep in mind, in this special case, we're calculating the sum of squared deviations from the population mean, not the sample mean. Let's continue by expanding this formula. Xi minus mu squared solves to xi squared plus mu squared minus 2xi mu. And we can now break this into three separate fractions. The sum of xi squared divided by n plus the sum of mu squared divided by n minus the sum of 2xi times mu divided by n. We'll come back to this equation in a moment. But first, let's also calculate a standard deviation for our sample. In this case, we are not trying to estimate the population standard deviation. We're just describing our sample, so we'll use n in the denominator, not n minus 1. This makes it a direct parallel to what we just did, but using the sample mean x bar instead of the population mean mu. We'll call this uppercase S because it's only descriptive of the sample. It's not the lowercase s, which is the estimate for the population standard deviation using n minus 1 in the denominator. Remember, that's what we're about to solve for. This can be expanded in an almost identical way to sigma squared. And as with sigma squared, we'll break this into three separate fractions. The sum of xi squared divided by n, plus the sum of x bar squared divided by n, minus the sum of 2xi x bar divided by n. We'll also reference this again later. From here, it may get a little strange, but you'll see why we do this in a moment. We're going to go back to our unbiased estimate for sigma squared using a sample where we know mu. Now we'll add identical positive and negative versions of two pairs of fractions. Note that because these are positive and negative versions of the same value, for example, adding 3 and subtracting 3, they cancel out. And we're in fact adding 0 to the equation, leaving it unchanged. This may seem a little weird, but you'll see in a moment that by adding these pieces to the equation, it makes things more clear in the end. So we start with our estimate of sigma squared using a sample, but where we know mu. Notice again that we're using the sample size n in the denominator, not n minus 1, because we know the population average. Now we're going to add and subtract the sum of x bar squared divided by n. And we're going to add and subtract the sum of 2xi x bar divided by n. Now, let's shuffle the right side of the equation around a bit. We're not fundamentally changing anything, just moving things around so they're clearer. After doing so, notice that the three fractions on the left are the same as the equation for s squared. We'll substitute s squared for those terms. Now we'll do a little mathematical manipulation of the final four fractions on the right-hand side of the equation. First, we'll move things out of the summation sign when possible, or eliminate summation signs altogether if that's possible. Starting with the first fraction, mu squared is a constant. The population average is the same for everyone. So we can move it out of the summation sign and it becomes n times mu squared. Moving to the second fraction, 2 times mu is a constant. Again, it's the same value for everyone. So we can move it out of the summation sign and it becomes 2 mu times the sum of xi. Moving to the third fraction, x bar squared is a constant. Again, everyone in the sample has the same sample mean. So we can move it out of the summation sign and it becomes n times x bar squared. Finally, in the fourth fraction, 2 times x bar is a constant, so we can move it out of the summation sign and it becomes 2 times x bar times the sum of xi divided by n. Now let's return to the first fraction. N in the numerator and denominator can cancel out. The result is simply mu squared. In the second fraction, 2 mu can be taken out of the fraction, but that leaves us with sum of xi divided by n. What is the sum of xi divided by n? It's simply the mean of x. So we can replace the sum of xi divided by n with the mean of x. In the third fraction, n in the numerator and n in the denominator can cancel out. The result is simply x bar squared. In the fourth fraction, 2x bar can be taken out of the fraction, but that leaves us with sum of xi divided by n. And the sum of xi divided by n is simply the mean of x. So we can replace the sum of xi divided by n with the mean of x. That leaves us 2 times x bar times x bar, or 2 times x bar squared. We can go even further. Notice that the final two terms, negative x bar squared plus 2x bar squared, reduces to plus x bar squared. Now for clarity, we'll have these two terms swap places. If you look closely at the final three terms and think about it for a while, you'll notice that they can be rewritten as x bar minus mu quantity squared. Now by this point, you may have noticed something. S squared, our estimate of the population variance based on our sample and sample mean, has to be too small as an estimate of sigma squared, the true population variance. Notice that the expected sigma squared is equal to the S squared plus something else that is squared. And something else squared must be positive. So S squared must be smaller than the expected sigma squared. But how much smaller? Let's find out. Now remember, the standard error of the mean, the standard deviation of means for an infinite number of samples size n from the population, is sigma divided by the square root of n. We can square that to obtain the variance of the mean. Another way of thinking of the variance of the mean is that it's the expected squared difference between a sample mean and the population mean. Mathematically, that's expressed as the expected value of x bar minus mu squared. Seeing the link between x bar minus mu squared and sigma squared divided by n, we can go back to our expected value for sigma squared and replace x bar minus mu squared with sigma squared divided by n. Sigma squared is the expected value for sigma squared, so we'll replace sigma squared with the expected value for sigma squared. And we'll subtract the expected value of sigma squared divided by n from both sides of the equation. With a little mathematical manipulation, we see that the expected value of sigma squared minus the expected value of sigma squared divided by n is equal to 1 minus 1 divided by n times the expected value of sigma squared, which is equal to n minus 1 divided by n times the expected value of sigma squared. Now we're almost there. We multiply each side of the equation by n divided by n minus 1. On the left, n divided by n minus 1 and n minus 1 divided by n cancel out, leaving us with the expected sigma squared equal to s squared times n divided by n minus 1. We now recall the original formula for s squared, the sum of xi minus x bar squared divided by n. We substitute that for the s squared in our equation. The n in the denominator and the n in the numerator now cancel out, leaving n minus 1 in the denominator. This leaves us with the result we anticipated. The expected value of sigma squared is the sum of xi minus the sample mean squared divided not by n, but instead divided by n minus 1. While you will likely never need to go through these steps yourself, it helps to be able to see that there really is a mathematical basis for dividing by n minus 1 instead of by n. It doesn't just come out of nowhere. So I hope you found this presentation informative.